Hi, this lesson is about the derivative of a function. So what is the definition of the derivative? So we're going to use this notation. This is read as f prime of x. So the definition of the derivative, f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. Remember, that means that's the limit of what we call the difference quotient. The expression in the orange box is called the difference quotient. Differentiation is the process of calculating the derivative. Remember that the derivative, y prime or f prime, also stated as dy over dx, that's three different notations you can use to denote the derivative. This represents the slope of the tangent line to the curve. Okay, so in other words, you can be asked to find the derivative in a variety of different ways. You can say, the directions might say find the derivative or differentiate the following function or find the slope of the tangent line to a curve. Those are some of the ways that you may be asked to find the derivative, as well as terms like find the instantaneous rate of change or the instantaneous velocity. So you'll see a lot of different ways where you're being asked to find the derivative. So let's use the definition to find the derivative of this linear function, y equals 6x plus 3. So when I apply the definition above to that function, I get the limit as h approaches 0 of 6 times x plus h plus 3 minus, and in parentheses, the function 6x plus 3. So when you distribute the 6 and you distribute the negative, everything will cancel except for 6h over h. But then the h's cancel, and so you're just left with the limit of a constant, and the limit of a constant is just that constant, so your limit value is 6. Now remember, that makes a lot of sense because if the slope of the tangent line is the derivative, well, this function happens to be a line, and the slope of this line is 6, so any tangent line would be the line itself, so it makes sense that these two numbers are exactly the same. So whenever you have a linear equation of the form y equals mx plus b, your derivative, no matter what those numbers are, is just going to be m. All right, so here we want to find the general expression for the slope of the tangent line to the curve y equals 1 over x, and then we're going to evaluate that slope at x equal to negative 1. So this time my function is a rational function. I have to apply the definition above. So y equals 1 over x, the derivative will equal the limit as h approaches 0 of 1 over x plus h. So that's the f of x plus h part of the definition, minus f of x, so that's the minus f of x part of the definition, and don't forget the whole thing is over h. So when we move on, I then have to get a common denominator for that numerator, and the common denominator for 1 over x plus h minus 1 over x is this. So the first expression gets multiplied by x over x, and the second one gets multiplied by x plus h over x plus h, which is exactly what you see on this line. But notice I also wrote the divided by h that you see here with this notation. It means the same thing, saves a little bit of space. So in the next line, because I now have a common denominator here, I distributed this negative and wrote it as a single fraction. So I have x minus h over the common denominator. And I also rewrote division as multiplication and took the reciprocal of the second expression. So it's times 1 over h. Okay. So now you can see that from this line to this line, the x's cancel, so these two cancel. So I'm just left with negative h over x times x plus h times 1 over h. But then the h's will cancel. So this h cancels with this h. So I'm left with this line. And at this point, I can let h equal 0. So in other words, apply direct substitution to your limit. So when I apply direct substitution, you get what you see here. Notice that you no longer write your limit in front of the function once you apply direct substitution. So your final answer is that your derivative is negative 1 over x squared. All right, so let's do another rational function. This one's a little bit busier because I have x's in two places. I have f of x equal to 5x over x minus 4. So in addition to finding the derivative, we're then going to find the values where the function is differentiable. There is going to be some restrictions because this is not defined for all real numbers, and my derivative will also have some places where it doesn't exist. So just like in the last problem, when I put it, use the derivative for the definition for the derivative and apply it to this function, I get 5 times x plus h over x plus h minus 4 minus f of x, which is just 5x over x minus 4, and then the whole thing is divided by h. Just like the last one, I need an LCD. So that's x plus h minus 4 times x minus 4. The first expression gets multiplied by x minus 4, which is what you see right here. And the second one gets multiplied by x plus h minus 4, which is what you see here, all over our common denominator. And just like in the last problem, I wrote divided by h instead of like this, I wrote it like this. Again, saves a little bit of space. And then on the next line, I did several things. I FOILed this, and I distributed the negative 5x, and I rewrote divided by h as times 1 over h. Do not expand this denominator. Leave it as is. That will be the case anytime you're using the definition to find the derivative. You want to leave that denominator as is, but definitely work out the numerator. Distribute, FOIL, combine like terms, and try to cancel as much as possible. So here several things will cancel. The 5x squareds cancel, the 20x's cancel, the 5xh's cancel. So I'm just left with this expression right here. And then you can see that this h cancels with this one. And at that point, I will be able to apply direct substitution, plug in h equal to 0 into that denominator. And so I'm left with just negative 20 over x minus 4 to the second power. So that's the general expression for the derivative. Now, where are the values? Where does the derivative exist for this function? So f prime of x exists for all real numbers except at 4. Because if x is 4, I would be dividing by 0, which is the same place that your function does not exist. So f prime of x exists on the interval from negative infinity to 4, and then again from 4 to infinity. All right, so there are some linearity rules of the derivative. Those rules, the first one states that if you're adding two functions and taking the derivative of it, that's what that means. The derivative of f plus g is the same as taking the derivative of f and adding that to the derivative of g. So you can do them separately. Same is true for subtraction. The derivative of f minus g is equal to the derivative of f minus the derivative of g. And when you have a constant c, c times f, the derivative of that is the same as taking the derivative of f and then multiplying it by c. Okay, so we cannot apply these rules, the same idea, to a product. So in other words, the derivative of f times g is not the same as the derivative of f times the derivative of g. That is not true. And it's also not true for quotients, the derivative of the derivative, sorry, I'm using the wrong notation here. The derivative of a quotient is not equal to the derivative of f divided by the derivative of g. In fact, you're going to learn two other rules for products and quotients later on in the course. So be careful not to make that assumption. That is not true. So just like I mentioned before, here are some of the ways you might be asked to find the derivative. You might see the directions differentiate, find the slope of a tangent line to a curve, find the instantaneous rate of change of one variable with respect to another, find the instantaneous velocity of a particular at a particular point in time, so at a particular time value, so a single time value, or find the instantaneous acceleration of an object at a particular point in time. So all of these would mean to find the derivative. And again, as I mentioned before, there are different notations to find the derivative. Y prime means find the derivative. This one, dy over dx, also means to find the derivative. This one might look familiar. It looks sort of like one that we've been using for a while now since algebra, which is delta y over delta x, change in y over change in x. Remember, a derivative is a slope, so that's why these two look similar, because they are associated with each other. And then it could be expressed in terms of f, the derivative of f with respect to x, the derivative of f of x with respect to x. This is another common notation, the derivative of f of x, or this notation, the derivative of f of x, and just pointing out with respect to x. So you might see a combination of these being used in my lessons, in different textbooks or other videos. You can think about this notation as a ratio of two expressions, and actually we will be talking about them individually later, the numerator and the denominator, when we talk about a concept called implicit differentiation and regarding differentials. So you will we'll be kind of looking more closely at what this notation actually means. Now we have higher order derivatives, which means you can take a second and third and a fourth derivative. So with one tick mark here, that would be the first derivative. Two little tick marks in between the f and the x, that means the second derivative. But with some of the other notations I mentioned above, it could be stated like this. Third derivative, and anything higher than 3, you would be writing a little number in the upper right-hand corner. So for example, the fourth derivative would be written like this, the fourth derivative of x, or sometimes they put it in little parentheses. That would mean the fourth derivative of f of x. So in order to find higher order derivatives, you have to go in order. If I was asked to find the third derivative, I would have to find the first one, then the second one, and then finally the third one. So let's find the first and second derivative. So this is f prime and f double prime. So you can call this f double prime of x. For f of x equal to the quadratic function x squared minus 3x. So again, I'm using the definition of the derivative to find f prime first. So I have the limit as h approaches 0 of x plus h to the second power minus 3 times x plus h minus, and then parentheses x squared minus 3x, and the whole thing over h. So here you have to FOIL. Here you have to distribute the -3, and here you have to distribute a negative. So that's exactly what was done on the second line, and the denominator stays the same as just h. Okay, but when all of that is done, several things cancel in the numerator. The x squareds cancel, the 3x's cancel, and then I'm left with 3 terms with h's in them. And so I could factor that out. When I factor that out, I'm left with h times 2x plus h minus 3 all over h. But then at that point, the h in the numerator will cancel, the h that was factored out in the numerator will cancel with the one in the denominator. So I'm left with the limit as h approaches 0 of 2x plus h minus 3. Here we can apply direct substitution. Just plug in the 0 right in there. And you have a first derivative of 2x minus 3. Now to find the second derivative, my function is now 2x minus 3, which is linear. So if you remember what I said at the beginning of the lesson, the derivative of a linear function is always going to be the slope. So my answer should be 2. Okay, but let's show the work for it. So I applied the definition of the derivative here. The limit as h approaches 0 of 2 times x plus h minus 3 minus 2x minus 3 in parentheses. Distribute the 2, distribute the negative, and I'm left with this line. Several things cancel, so the 2x's cancel and the 3's cancel. I'm left with 2h over h. The h's cancel, so I'm left with a constant, and so just as we expected, my second derivative is equal to a constant of 2. Okay, so let's go on with this lesson. So not all functions are differentiable. The following are where a function would not be differentiable. So for example, a function is not differentiable wherever there is a corner or a kink in the graph. So an example of that would be the absolute value function. So if you recall, the absolute value function looks like this V. And so where the two lines meet, that's considered to be a corner. So although it is continuous and the graph exists at 0, it is not differentiable at the corner 0. So I mentioned that here. It is continuous, but it's not differentiable at 0. It's also not differentiable at any discontinuity and at any point where there is a vertical tangent line, which remember is a type of discontinuity. So for example, in this picture here in green, it's discontinuous. There's a jump discontinuity at -2, and there's an infinite discontinuity at +3. So it's not differentiable at -2 and at +3. Okay. So find the points where the slope of a tangent line to the curve y equals 8x minus x squared has a slope of 6. So again, here we're solving for a point, which means an x and a y value. And you're told that the slope of the tangent line is 6. Remember, the derivative is equal to the slope of the tangent line. So that's exactly what I need to solve, y prime equal to 6, in order to solve for x. And once I find x, I can plug in to the original function to get my y, to solve the question, to answer the question. So my function is a quadratic. I again use the definition. Just like in the previous examples, you distribute and FOIL. Lots of things will cancel. So the 8x's cancel, the x squareds cancel, and I'm left with 3 terms with h's in them. I factor that out, which means that the h in the denominator will cancel with the h that was factored out. And so I'm just left with the next line. So these two cancel. And when I plug in 0 in here, I'm just left with 8 minus 2x for y prime. But remember, we set that equal to 0. Equal to 6. So we're solving this equation. Subtract 8 from both sides, and I get negative 2x equals negative 2. So that means that my x value is 1. And in order to solve for the point, I plug in 1 into the original equation, which was 8x minus x squared. If you remember, that was the original. So I plug that in, and I get that y is 7. So the point where the slope of the tangent line is 6 is the point 1, 7. Okay, so as a reminder, if we call s of t your displacement function, then the derivative s prime is your instantaneous velocity, and we use the notation v of t. And the second derivative would be the derivative of v prime, which is acceleration, so we use the notation a of t for that. So that would be the instantaneous acceleration of the function. Okay, so let's do a problem regarding displacement. So find the instantaneous velocity of an object moving with rectilinear motion according to the function s of t equal to 3t squared minus 2t cubed. So that means I'm going to be applying the definition of the derivative in order to find velocity. So this time I have a third degree polynomial. So when I use my definition, you'll have, for the first part, 3 times t plus h squared minus 2 times t plus h to the third power minus, and this is just minus s of t, so minus the function that was given, all over h. So I need to FOIL and distribute the 3. So I did that here. So I get 3t squared plus 6th plus 3h squared. And then here, t plus h to the third power means that you are going to multiply t plus h times t plus h squared. So that's exactly what I did. And don't forget there's a 2 in front of it. So here, what I did was I FOILed this and I distributed 2 across to this one. So that gives us what you see here in the that was circled. And then the second part is just s of t. So on the next line, I distributed 2t across, and then I distributed 2h across, and I get all of this. And I also distributed the negative. So on the next line, I distributed this negative. So all of these signs change to a minus. And then many things will cancel. So the 3t squareds cancel, the 2t cubes cancel, I think I wrote everything else. Oh, the 4t squared h cancels. No, wrong place. I combined like terms here. So the 4t squared h gets combined with the minus t squared h. So that's where this negative 6t squared h comes from. And the negative 2th squared combines with the negative 4th squared, again, to get the minus 6th squared. So there is a slight difference between them. And then the minus 2h squared. So everything left in the numerator here has a common factor of h. So if I factor that out and cancel it with the denominator, you are left with this limit, which means that I can now apply direct substitution. So anything with an h will go to 0. So this one goes away, this one goes away, and this one goes away. I'm left with this as my general expression for velocity, 6t minus 6t squared. Okay, so here's another one regarding, this one is regarding velocity and acceleration. So use the definition to find an expression for the instantaneous acceleration of an object moving in rectilinear motion, where v is the velocity, s is the displacement, and t is time. Well, you're given the velocity function and you're asked for the acceleration, so the derivative of velocity is acceleration. So when I plug that into the definition, first replace the t with t plus h, and then minus v of t all over h. So this time I end up with two radical expressions with a minus sign in between. So what I'm going to do is multiply numerator and denominator by the conjugate of this expression, which means same two expressions with opposite sign in the middle. So I'm going to be adding. And notice that I also distributed the 2 across the t and the h. So now I'm ready to FOIL this. And these two are just going to be written next to each other. So that's exactly what you see in this denominator. And when I FOIL my numerator, a square root times the same square root just gives you the expression on the inside, the radicand, minus, same idea, same two radicals being multiplied together. So I'm left with minus 2t plus 1. So when I distribute this negative, the 2 t's and the 1's will cancel, so my numerator is just 2h over my denominator. The h's will cancel, so I'm left with the limit of this expression. And at this point, you can apply direct substitution, and when I do, the 0 goes there, so this term goes away. So I'm left with square root of 2t plus 1 plus square root of 2t plus 1 in the denominator. So there's 2 of them. So that's 2 over 2 times square root 2t plus 1. But if you simplify, the 2's cancel. So my acceleration is 1 over the square root of 2t plus 1. So if you're given displacement and you were asked to find acceleration, so if given the displacement and asked to find acceleration, you must take the derivative 2 times. So the first derivative would be velocity. The second derivative would give you acceleration. So you have to pay attention to what's being asked so that you know how many times you need to take the derivative. Okay, graphical interpretation of f of x and f prime. So any function f of x and its derivative f prime can be graphed, as well as any higher order derivative like f double prime, f triple prime. And remember, there's a relationship between a function and its derivative. So since f prime represents the slope of the tangent line, for any interval on f where the slope of the tangent line to the graph is negative will correspond to f prime being below the x-axis. So remember, values below the x-axis are negative. Anything below the x-axis is negative, above it's positive. So f prime would be negative when the slope of the tangent line of f of x is negative. And then for any points on f of x where the slope of the tangent line is positive, then f prime would be above the x-axis. Any point on f of x where the slope of the tangent line is 0, meaning it's a horizontal tangent line, then f prime would equal 0. Remember, a slope is a derivative. And then the same relationships exist between f prime and f double prime, etc. So this is a sine analysis of 3 functions: the original function, the first derivative, and the second. Okay, the original function is in black, the first derivative is in red, and the second derivative is in green. Okay, so notice that when I am on the black curve, the function, any graph to the right of this point here, let's call that point A, and let's call this one here point B. So A and B. Anything to the left of A is going to have a tangent line with a slope that is positive. Notice that f prime is positive everywhere to the left of A. So all these values here are positive y values for f prime. Anything to the right of A but before B, so between A and B, tangent line there is going to be negative. So notice that everything from here to there will have a negative slope, but that's exactly the same places where the value of your f prime, or your, looks like a parabola, are below the y-axis. Anything greater than B would again be positive, a positive slope. So therefore, f prime has positive y values. The same relationship exists between f prime and f double prime. So between the red curve and the green curve. So let's call this one point C, where it appears the vertex is. Anything to the left of C is going to have a negative slope. The line is going downward from left to right, everywhere from negative infinity all the way up to C. But that's exactly where my line is below the y-axis. Remember, this goes on and on forever. This continues on and on forever. So it will be negative anywhere to the left of C. But when I am on the right side of C, my tangent line is positive, meaning the slope is positive. And you can see that anything to the right of C, my line is positive. So let's look at another example where we're doing a sine analysis. Sketch the graph of 1 over x and y prime. So the first derivative of 1 over x is negative 1 over x squared. So let's say y is in red and y prime, its derivative, is in this darker blue. So let's look at 1 over x. When I am on 1 over x, any point on that red line is going to have a negative slope. And you can see that my blue curve is below the y-axis everywhere where my derivative here is negative. When I'm on this part of the curve and I look for the slope of a tangent line, everywhere on that curve, my slope is also negative. It's going downward from left to right. So again, y prime, which is this piece, is below the y-axis. Here's another one. It's a quadratic, a linear, and a constant. So my quadratic is in red. My f prime, which is a linear function, is in blue. And f double prime is in green, and that's a constant of 2. So just like I explained before, on the red curve, I have a vertex for the parabola at 0, 0. Anything to the left of that is going to have a negative slope for a tangent line. And you can see that anywhere to the left of the vertex, my line is below the y-axis, therefore negative. This is, below the x-axis. Anything to the right will have a positive slope, and therefore my line is above the x-axis. And then looking at f prime has a constant slope because it is a line. It's got a constant slope of 2. It doesn't change as you move along the line, and therefore its derivative is a constant, and a constant is drawn as a horizontal line. 2 is positive, and therefore this horizontal line goes through the value of 2, a positive value. Okay, so that's it for this lesson. Give the homework a try. Good luck.